We've discussed the image of why we need a dedicated DC offset calibration for a strong arm latch, preamplifier, summer, and CTOE, but we never dived into what the DC offset calibration or reduction technique was, which was called trimming. Therefore, let's review why we need the DC offset reduction or mismatch reduction through the trimming technique. Before talking about how the trimming reduces the offset and its advantage, let's review how the dedicated DC offset reduction was achieved in the sample. In the strong arm latch, we could add another DC path differential input and connect to the differential output P and Q. From this green trimming, what are the trimming parameters? Think about the images of voltage in and current out for 5 seconds. Correct. Another trimming GM cell can trim the GM mismatch of the signal path at the M1 and M2 as shown here through the trimming the input voltage such that the output current can be adjusted. But when and how the trimming procedure was done? Bingo! From the previous samples trimming exercise, you must have a brief idea of the trimming technique, which is to adjust the value of any critical parameters, such as GM here, from an added on-chip component to reduce the mismatch. Therefore, the added on-chip component must be low capacity, low power, and low impact on the speed. In addition, the system must provide any on-chip elements with memory, such that the mismatch reduction of the trimming result or values can be stored somewhere to apply the values when needed later. Let's review the general offset concept and understand what caused the offset. Then we may know where to trim those mismatches to reduce the offset further. First, if we shorten the differential input of an ideal amplifier, the output voltage should be 0, since Vout equals Vin times A, while the Vin equals 0. However, second, if we shorten the differential input of a real amplifier, the output voltage must be non-zero, since Vin is non-zero, which was the input offset from the mismatch of the differential topology. Lastly, and unfortunately, the differential mismatch not only causes the input DC offset, but also results in low common mode rejection ratio (CMR) and low power supply rejection ratio (PSR). Therefore, the mismatch or offset reduction is a must. What kinds of differential mismatch do we need to trim? Think about the differential amplifier images for 5 seconds. Yes, the ideal fully differential amplifier shows transistors M1 equals M2 equals M. Resistor rows R1 equals R2 equals R. Therefore, there's no mismatch or offset as we talk about. But a real fully differential amplifier shows M1 does not equals M2 and R1 does not equals R2, such that the mismatch causes the offset. Why would the real amplifier have the mismatch? Think about the manufactured images for 5 seconds. Bingo! It's impossible to perform the semiconductor doping exactly everywhere. Also, the lithography should have errors and cause a rough surface. Lastly, the different mechanical stress on the chip will cause the semiconductor's property to be different, not to mention the packaging process will result in non-uniform stress levels. So, we must accept the mismatch or offset and try to reduce the mismatch as low as possible through low-cost solutions without speed and design overhead, which could be the trimming technique from our simpler experience. Let's walk through the trimming of the general differential amplifier. Let's correlate the input offset with the mismatch from the transistor and resistors. First, the threshold voltage difference, delta VTH, between the M1 and M2 is exactly the input offset. Interestingly, the threshold voltage difference or variation will depend on the dimension as the channel width and channel length, or even oxide thickness of the process. So, delta VTH is temperature independent. Second, the output DC current divided by GM mismatch due to the mu C oxide W over L mismatch contributes to the input offset as well. Lastly, the resistor mismatch will cause the output current mismatch from CCL, so the input offset will be delta I divided by GM. Unfortunately, the ID over GM is a temperature-dependent factor and may limit the trimming accuracy. But why? Think about the temperature variation images for 5 seconds. Correct. To reduce the trimming complexity and cost, we usually only measure and trim the offset at one temperature, T-trim1. But then the amplifier may be heated up or cooled down to other temperatures, T up 2 or T up 3, which may raise the input offset again, even though the offset was reduced near zero at T-trim1. To make the 1-point trim in temperature work well, we must make sure the GM and ID are proportional to each other over temperature, which constrains the differential pair's operating point to be biased at a deep weak inversion. Otherwise, the 1-point trim may not get the offset as low enough over temperature after offset trimming. Furthermore, we don't want to increase the trimming cost by adding multi-point trim. Here are the summarized images of why DC offset reduction or mismatch reduction techniques through trimmings. We started with our original simpler DC offset reduction idea, which is a trimming technique at the GM cell without degrading the sampler speed. Therefore, the trimming technique is to adjust the value of any critical parameter, for example GM here, from an added on-chip component to reduce the mismatch. However, the added on-chip component must be low complexity, low power, and low impact on the speed. Furthermore, the system must provide an on-chip element with memory, such that the mismatch reduction of the trim results or values can be stored somewhere to apply the value when needed later. The general offset concept let us know where to trim those mismatches to reduce the offset and CMR, PSR further due to doping variability, lithography error, and unbalanced stress. A traditional input offset comes from the transistors and resistors. For example, the threshold voltage difference, delta VTH, between the M1 and M2 is exactly the input offset. Second, the output DC current divided by the GM mismatch due to the mu C oxide W over L mismatch contributes to the input offset as well. Lastly, the resistor mismatch will cause the output current mismatch, so the input offset will be delta I divided by GM. Unfortunately, the ID over GM is a temperature-dependent factor and may limit the trimming accuracy after heating up or cooling down away from the calibration temperature. What we can do is to constrain the differential pair's operating point to be biased at the deep weak inversion to reduce its temperature coefficient of ID over GM, such that we can keep a low-cost 1-point calibration without degrading the offset accuracy over temperature. Thanks for watching. Before you go, if you are benefiting from those key images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.